For number 17, be careful. You might think they're looking for the maximum or minimum area of the rectangle, but they're really looking for the minimum of the shaded region. So we could let S equal the area of the shade, which would be the area of the entire parabolic mound minus the area of the rectangle. The area under the cosine curve will be the integral, and the area of the rectangle will be base times height. Blah, 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 blah. Okay. All right, so cosine, we know, has zeros at negative pi over 2 and pi over 2. And the rectangle's height is the y value of this curve, which is cosine of x. And its base, this dimension is from here to here. If we go x to the right and cosine of x up, then the width of this rectangle is x plus x, or 2x. All right, so this will be the area of the shaded region. Let's go ahead and evaluate this. Doing the definite integral, we get this, which is 1 minus a negative 1 with the fundamental theorem of calculus, which is 2. And the area of the rectangle was 2x cosine of x. So we have our function for the area of the shaded region, and we want to minimize it. Let's find the derivative. The derivative will be 0, and then the derivative of minus 2x cosine of x, we'll go ahead and use the product rule. So we get that. We'll set that equal to 0 and use our calculator. Finding when the first derivative is 0 will alert us to any critical values where we might find our relative minimums and maximums. If you graph this derivative with zoom trig, we've got a bunch of zeros, but we really are only looking for zeros that exist between x equals 0 and x equals pi over 2. So let's change our window a bit. And this is where we have a relative minimum or maximum. I should say this is where we have a critical value, when x is 0.86033. Now in my calculator, we're using registry y sub 1 for our first derivative. So if we just show that the first derivative is equal to 0 when x is 0.86033, that's a critical value. To show whether it's a relative maximum or minimum, we can use the second derivative test. Remember, the second derivative test allows us to see if a critical value is a relative minimum or maximum. What is the second derivative at 0.86033? If it's positive, then we have ourselves a relative maximum. And if it's negative, then we'll have ourselves a relative minimum at this x value. We can use our calculator to quickly find the value of the second derivative of y1 of s, which would be the first derivative of y1. Using my calculator, the derivative of my first derivative, which is my second derivative, when x is 0.86033 at that 0, the critical value, is positive. We were asked to find the minimum value of the shaded area. We've defined S as the shaded area. We don't know what the minimum is yet, but we know that it has a minimum when x is 0.86033. So now we'll just substitute this value into our function for the area of the shaded region, and we will have the minimum shaded region for this context. And our shaded area is 0.8778, which is choice B. That concludes number 17. On the other hand, there's always more than one way of approaching these problems. Another way to do this problem would just be to find the area of the parabolic mound. And if you're looking for the minimum shaded region, then you could just separately find the area of the rectangle. And we'll minimize shade when we've maximized the rectangle. So you also could have just done this. The area of the entire parabolic mound, and again, this is a calculator problem, so you wouldn't even have to show the work, is 2. You should show this expression, and then you can just use your calculator and write down the answer 2. The area of the rectangle, which we're going to maximize, thereby minimizing the area of the shaded region is base times height. And now we want to maximize the area, so we will be minimizing the shaded area. Maximize the area of the rectangle so that we minimize the area of the shaded region. All right, what's the maximum area of the rectangle? There's the derivative of the area of the rectangle. When we set that equal to 0, guess what we get? An x value of 0.86033. So the area of the shaded region will be 2 minus the area of the rectangle when x is 0.86033. And we get the same answer, choice B, once again. So whether you think of it as a function for the entire shaded area, which you then do the calculus to find the minimum value, or you'd think of it in parts, the whole, the rectangle, maximize the rectangle so that the shade is minimized. They are both logically equivalent.